lecture 8.5, determining the locations of minimas, maximas, and partial maximas. In interference, almost always one can use the small angle approximation. However, this is not the case for diffraction. And this is something that I'll show you why. This means that two equations must be solved to determine the angular and screen locations of a minima slash maxima, or in that case, a partial. And these two equations are, there's the path difference equation, which is a sine theta of n equal to n lambda, and the screen location, which is y of n d tan of theta. Those are the two equations. The process goes something like this. Now, when I say the process goes something like this, sometimes, you're going to have to use a slightly different format, but you still have to deal with these two equations. So typically, the first thing that you do here is that one identifies which minima maxima or partial by knowing the n value. In other words, you calculate n max and then you're going to figure out where you're at. And then two, use the path difference equation to solve for theta of n. In other words, you have a sine of theta n lambda, but note, you know the n value. You typically know the diffraction parameter, so this allows you now to isolate theta. And this gives you sine inverse of nd over a over lambda. And then this guy right here, this is now the angular location of the minimum, maxima, or the partial. 3. Now what you want to do here is that you want to sub this into the screen location. Equation. In other words, you're going to take that angular location and now you have this. So those are the things here. So what we're going to do here is that we're going to look at some examples. So let's go through some examples. Where we take two different processes to calculate one. I would say one thing that we can do here is that we could get the angular and screen locations of all minimas and maximas. This is a very standard process. And then we're going to take a slight change here and we're going to say you're now given some particular screen location. What is its location in the diffraction pattern? Now, let me be careful. A lot of the times when we say location, we really mean its n value. What is its n value in the diffraction pattern? And then from that, we're going to ask, is it a minimum, a minima, a maxima, or a partial maxima? So let's break those two situations down. And we'll use the applet, the pentaplet, to actually compare to see how we do. So the first thing that we want to do is that we want to predict the angular and screen locations. So I need to give some values in order to do that. So what we're going to do here is that we're going to set A equal to 1710 nanometers. Lambda is going to be 570 nanometers. And the screen distance is going to be 1.5 meters. So these are the values that you have to assume in order to do these calculations. Otherwise, you wouldn't be able to do anything. As always, you have to start with the diffraction parameter. So starting with the diffraction parameter here's what we get. We know that the diffraction parameter gives us n max, which is then A over lambda. So if I plug in my values, I get exactly 3. So you know that that 3 right there is automatically telling you that the endpoint has to be a minimum. So I'll write this down. I know that we just covered that, but we need to go through this process. So here we go. So the first thing I want to do here is we want to go find. So how do I want to do this? I think I'm going to go, the first thing I'm going to do is I want the angular and screen locations of the minimas. Okay. So if I want the screen location, then I have to start going. So the first thing that I said here is that since n max is an integer, from last lecture, this implies that the end of the diffraction pattern is a minima. So that we know that at 90 degrees, we have a minima. So then this immediately tells us the number of minimas. So the number of minimas goes like this. So we know that ND goes as plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. But at this point, we exceed, right? We have exceeded n max equal to 3. So the sequence stops. So then this tells us here right away that ND is equal to 3, and the number of minimas then has to be 2 times 3, which then gives us 6 minimas. Again, we've done this, but we're just doing this all over again in the context of calculating angles. So now that I know that, now I want to go use the path difference equation to get the angular locations. So now what we're going to do here is that we're going to use the path difference equation to calculate angular locations. So we go a sine of theta n, that has to be nd lambda. So then solving for theta here, maybe we should do this in a couple of steps. So then sine of n has to be plus or minus nd divided by a over lambda. And then we could see here is that I'm going to take my n values. And so I'm going to go, this is going to be plus or minus 1/3, plus or minus 2/3, plus or minus 3/3. So then from here, we see that theta of n, when I take the inverse of this, is then going to be this plus or minus nd over a over lambda. And then I'm going to get that theta 1 is then going to be plus or minus 19.5 degrees. Theta 2, that is punching this into my calculator, 41.8 degrees. And then finally, theta 3 is going to be plus or minus 90 degrees. So what I'm seeing here is that these are the angular locations of the minimas. Now, let's look at this thing here. Okay. What I want to look at is I want to look at this, I want to check the small angle approximation. So one of the things that we said here is that a key separation between interference, which allows the small angle approximation the vast majority of the time, versus the fraction, which does not allow the small angle approximation. Let's see if we can validate that statement. So let's check if the small angle approximation, in other words, sine of theta is equal to theta, used in interference is valid for diffraction. We have two angles to check. Well, we know 90 degrees is not a small angle, so that doesn't make any sense. So here we go. So we have, so sine of theta 1, which is sine of 19.5, this guy is equal to 0.33 versus theta 1, which is 19.5 degrees, but then I got to convert that into rads. So this now is 0.34. So when I look at this, you can see here that this matches up pretty good when you're close to the central max. So I would say that this is a good approximation. And what you're going to see, since it's 3% off, I think that's a really good approximation. But now let's look at the next angle. Now what I'm going to have is I'm going to have sine of theta 2, which is then sine of 41.8. And if you compute that, that is 0.67 versus theta 2, which is 41.8. And again, I got to do the conversion. And I'm getting 0.73. So what you're seeing here, so if I compare this to this, well, you could see that it's not so good, since its difference is 9%. So you could see that it's already failing as you get to, as you move away from the central axis. So what I want to do here is that what I'm going to do now is that I'm going to use the Fint applet, and there's only one in this chapter, the Fint single slit applet, to compare angular locations. So let's go look at that. So if I go to the Fent applet, what you're seeing here is that I've already put in 570 and 1710. And what it does here is that you could see that there's the diffraction pattern. And then it has this, but with an angular screen. Now, if I click here, it lists all of the minimas here. So what I'm going to do here is that I'm going to take this and I'm going to insert it into my screen, my OneNote. So if I go back, then I'm going to come in and I'm going to look right here. So what did we just see here? I'm going to paste this guy right here. And for comparison, I'm going to take these guys and I'm going to bring these down with me. And I'm going to paste these guys right here. So what am I seeing here? Well, let's look at the minimas. So here's a minima here, and then there's a minima right there. Here's another minima, and then there's a minima right here. So if I label them, this will be -1, -2, -3, +1, +2, +3. So those are the 6 minimas. If you look at the diffraction pattern, you could see that here's 1, 2, and if you go to 90 degrees, you see that it's 0 there. Again, this is -1, -2, -3, +1, +2, +3. So the thing that I want you to compare is that these are the applet values. And then over here, these are our calculated values. And you could see that as we compare these two, they're exactly the same. And they should be the same. And the reason why they're the same here is because minima equations are exact. They're not approximations like we saw, like we've been talking about for maximas. So now let's go calculate the screen locations. And there's a couple of things that, there's one thing at least that we should talk about. So now the screen locations of minimas located at theta n equals to 19.5, 41.8, and 90 degrees are as follows. So I'm going to have y of n. Now that's d tan of theta of n. Now if I plug in my values, right, that's my screen location right there. Then I'm going to find that y of 1 is then going to be plus or minus 0.531 meters. Y of 2 is going to be plus or minus 1.34 meters. And then finally, y of 3 is going to be plus or minus infinity. Now the infinity, excuse me, the infinity distance might surprise some of you. Well, let's go look at what do we mean by it? So y is y of 3 equal to plus or minus infinity. Now, if we have a flat screen, which is exactly what we have in a lab situation, we have a flat screen and not a curved one. The endpoint at 90 degrees is at infinity. So to see this a little bit mathematically, you probably see this right away, but just in case you didn't, this is going to be y of 3, and this is going to be plus or minus 1.3 meters tangent of theta 3. But if you look at this, this is plus or minus 1.53 meters. This is going to be sine of 90, and this is going to be cosine of 90, which really gives you that this will be 1 divided by 0. And of course, this guy is undefined, and we define this by labeling this as infinity. So mathematically, that's why we're seeing that infinity here. But if I look at the screen here, what am I actually seeing here? Well, if I have my screen right here, and I'm looking at my pattern, let's say I look at just one of these, then that means here, in this case, I'm not going to really draw out the pattern, but you could imagine that if I had one that looks like this, that minima there is at infinity. So if I look at this point, and this is at 90 degrees, the distance from here to here is actually equal to infinity. And then, of course, on the other side, you got minus 90 degrees. Okay, so now that we've dealt with the minimas, let's go in and deal with the maximas. So now, let's repeat this process for the maximas. So here we go again. Now, since n max is equal to 3, then if I look at NC, NC can only take off, remember this is an approximate value, it can only take the 1/2 values, approximate 1/2 values. And so as I start to sum these, you could see here is that right here, it exceeds n max of 3. So the sequence stops here. So then this tells me here is that NC is equal to 2, and the number of maximas goes something like this here. So I'm going to get 2 times 2 plus 1 gives me 5 maximas. So we can see here that the central location or the central maxima is located at theta equal to 0 degrees. So it's NC equal to 1 and 2 that we need to calculate. So here we go. So then the angular locations are then going to be given by a sine of theta n. Now remember, this is an approximate equation. Okay, that's an approximate equation. So you know what? I'm going to move this down here. This is an approximate equation. So that being the case, now I'm going to isolate sine. So then I'm going to get sine of theta n. That's going to be approximate equal to plus or minus nc plus 1/2 divided by a over lambda. So if I plug in my values, I know that my n values have to be 1 and 2. So then this equals then, it's going to be plus or minus 1.5 divided by 3 plus or minus 2.5 divided by 3. And then that's the end of the sequence. So then if I focus on getting the angular location, we can then see that this would be sine inverse of nc plus 1/2. And this will then be, in this case, it's going to be 3. And if I solve for this, I'm going to get theta 1 is equal to plus or minus 30 degrees. And then theta 2. Now, let me be careful here. I got to keep stressing the fact that these are approximate. So let me move this back. These are approximate values. And then this is plus or minus 56.5 degrees. So here are my angular locations right here for my maximas. So the first thing that we want to do here is that we want to go check these. Okay. So what we're going to do here is that we're going to use the Fent applet again to check the values. So if I go and I look at this, here's what I'm seeing. What I'm seeing here is that you're seeing that if there's a link, if I click on the minimas, it gives you all the minimas. But if I click on the maximas, it gives you all the maximas here. You could see that there's one that's central. Then I have 28.5 and 55.1. So let me copy this and put it into my OneNote here. So here we go. So I'm going to come over here and I'm going to paste this right here. And what I want to do here is that I want to take these angular locations right here and I want to paste them right here. So according to what we just did here, here's what we found. We see here that we have a maxima right there, the central max. Then I have one right here. Then I have one right here. right here, and right here. So this is not a value, and you'll see that this is, oops, that's a little bit too thick. Let me get that thinner. This will be -1, -2, +1, +2. And again, if I look at them, you could see that I have, here's my central, then I have my first secondary, my second secondary. So this guy's going to be, ooh, that's not, yellow on yellow is not good. So I'll write it right here. This will be +1, and this will be +2. So the first thing that you should note here is that right here are the applet values. Over here, these are our calculated values. And you could see that they're not the same. So when I compare these to here, I would say that these are not the same. They're approximate. You could see that the first angle is at 28.5. This one calculates 30. The second one is 55.1, and this calculates 56.5. So there's a difference between the two. That's why we say here that these are approximate values. And in the next chapter, you'll see if we go to calculate the exact ones, that it's pretty complicated because you have to deal with the non-transcendental, a transcendental equation. So the last thing that we got to compute here is that we want the screen distances. So the screen locations of the maximas are, again, these are going to be approximate. You're going to have, this is going to be d tan theta of n, and we saw that this was 1.5 meters times the tangent of theta n, and then we're going to use those two angles. So then we'll see here is that the first location is going to be approximate, which we get plus or minus 0.814 meters. And then y2 will also be approximate, which will give us plus or minus 2.15 meters. Okay, so now we're done with one of these. Now let's go to the second one. So I'm going to use the same values as before, but now I'm going to go in a different direction. This is going to be 2. So assume now that we have a given screen location. Which is 1.48 meters. Where is this location in the pattern and identify if it's a minima, maxima, or a partial maxima. Remember that we're still using the same values. So remember, we are still using the same values of A, lambda, and D as before. So in other words, we know that n max is equal to 3. Right? We know that. We know that the diffraction parameter is 3. So here we go. So what we're going to do here is that we're going to start, or starting, with the screen location solve for the angular location theta. So I go y of n is going to be d tan of theta n. Now solving for theta n, I'm then going to have the tangent inverse. Now I'm going to put in my values here. So my value then will then be 1.48 divided by 1.50. And you could see here that that really forms a 45-degree angle. But if you calculate the details, this becomes 44.6 degrees, which is what we expected. Okay, so this guy here is what we have. So from the path difference equation, we can get the n value. So from the path difference equation, solve for the n value. So I'm going to get a sine of theta n, and this will be n lambda. So then if I isolate n, this is then going to be the diffraction parameter times the sine of 44.6 degrees, which will then give me 3 times the sine of 44.6 degrees, which then gives me 2.11 equal to n. So what we're seeing here, that this is a partial maxima since n is not an integer. If it was an integer, then the ending would be a minima or an odd half integer, which then the ending would be a maxima. So it's in between. So now if I go and I plot this diffraction pattern, we can locate n equal to 2.11. So again, we know that n, we already know that n maxima is equal to 3, so we can go right from that. So here we go. So what I'm going to do here is that I'm going to look at my diffraction pattern, and of course I'm only plotting half of it. So then I'm going to have 1, 2, and then 3. Those are my 3 minimas right there. And we've already seen, even from the applet, that that's exactly what we're seeing right here. So this is I relative. So this guy's 1, this guy's 2, this guy's 3. And again, if I start to add these guys, this is approximately 1.5. This is approximately 2.5. So that's my diffraction pattern. So when I look at this thing, what I'm seeing here is that this point right here, that little point is 2.11. So to really see this better here, I'm going to zoom in. So if I look at the second secondary, so I'm going to zoom in into the second secondary maxima, that is. So if I look at this, this is what I'm seeing. So this guy tells me that this guy is 2, this guy is 3, and then this one right here is approximately 2.5. So when I look at this thing, this is just past, right? This is 2.11. So this is just beyond the n equals to 2 minima. And therefore, closer to a minima and a maxima.